Hello. Good afternoon, guys. So this is lab 3, and so in the last lab, what we did was we just looked at how we'll train a basic CNN on. So we trained it on MNIST. So this time, we'll build upon that, and our goal is to learn how to apply a DL model on any computation problem. So whenever you're working with images or any kind of visual data, so let's stick to images for now. So assume you're working with some new data set that you created, but then last time we directly used the MNIST data set that was available with Torch Vision. So we won't have this. We won't have this functionality if you're dealing with a new data set. And so in that case, what we'll have to do is we'll have to build our own custom data set. We'll have to build a way to load the data set, and we'll have to make our own data loader. So we'll look at how we'll do that today on CIFAR 10. So CIFAR 10 is a pretty popular dataset, and the dataset is already available in Torch Vision. But we'll have a look at how we can make a custom dataset by ourselves and not rely on that, so that then you can use the same principles and apply it to any new dataset that you come across. And we'll also look at how to build. So last time we last time we used again a loss function that was already inbuilt to PyTorch, and so with this time we'll see if we want to have a custom loss function. So at some point you'll have to write your own loss function, and you will not be able to use the loss functions that's provided by Torch. So then, how do you go about doing that? We look at data augmentations. So how you transform data, we'll look at that, and then we'll also look at a few other things like learning rate schedulers and so on. Okay, so firstly, last time I did not cover what actually convolutional neural networks are. I did not motivate their use, and like a couple of people had messaged me saying that like it wasn't clear enough. So I'll just quickly go over like uh, why why do we use convolutional neural networks at all, and how they work. So so first of all, I think last time somebody had told me that if I share the notebook, then it'll be easier for you guys. So right, I'll share it, and if anybody wants to follow along, they can do that. Okay, cool. So imagine you have a data set, and the data set has images of shape, of dimensions, 256 by. Yeah, sure, that's fine. Okay. So say you have a data set, and this data set has images of dimension 256 by 256. So this 256 in height and 256 in width. So what this means in terms of actual data, how much data is there? There will be 3 times 256 by 256. So there's 3 values corresponding to each pixel, which says R, G, and B, red, green, and blue. And so we have this much information corresponding to one image. So these many numbers, and assume we are going to apply to this image a normal neural network. So what I mean by normal neural network is fully connected neural network. So this kind of thing. So say you apply a neural network, and so how many units will be there in the input layer? The number of units in the input layer will be 3 times 256 by 256, because you're going to flatten this out. You'll flatten this out. If you remember in MNIST, we had 28 by 28 image. We flattened it out into 1 by 784. In this case, it will be 3 by 784. You can again flatten it into 784 times 3, or whatever it is. So you flatten it, and you'll have that many input layers. And assume you have, so in terms of like a decent neural network size, assume you have 1,000 hidden units in your hidden layer, and let's just assume there's just one hidden layer. So if you have just one hidden layer, 1,000 hidden units, then just for so then how many weights will be there? Like, so the corresponding to each of these connections, because it's fully connected, how many weights will be there? So there will be 3 times 256 times 256, which are the number of input layers, input units, times 1,000. There will be these many connections. Let's assume there's no bias here. Let's assume that's all like there are no bias weights. So uh, so there'll be these many weights just corresponding to this single layer. Just between these two layers, there'll be these many weights. So like, so how much is this? This is like these many weights. So this is what units, tens, hundreds, thousand, 10,000, million, around 200 million. So this is like 200 million weights or parameters corresponding to just a single between these two layers, which is a huge amount. And so you have to keep in mind that you'll be loading all of this into memory, and so it's not really an efficient method if you, especially when you're dealing with images that are like bigger and bigger. So this is a pretty small image. So 256 by 256 is not a big image by any measure. You have higher resolution images now, 1024 by 768 or 4K, 4096 by. So like these are huge images, and so when you're applying neural networks to such kind of images, uh, then the size of a neural network will become bigger and bigger. So that is a big problem, and that is one motivation for using convolutional neural networks. That's one of the many reasons. There are many other reasons. A single reason, and one of the most important reasons, is just in terms of the number of parameters that you'll save by using a convolutional neural network. Okay, so how does a convolutional neural network actually work? So if you remember, we were looking at this GIF last time. So imagine this is your image. Imagine you have a 5 by 5 image. So this is 1, 2, 3, 4, 5, and this is a 5 by 5 image that you have. Now you want to perform you want to apply a convolutional layer on it. So it's a neural network layer, and you're going to apply it to this image. So how does this work? And after you apply this convolutional layer on it, the spatial dimensions will decrease. So initially it was a 5 by 5 image, and after you apply to it, it will become a 3 by 3 feature. It will become a the feature size will be 3 by 3 in this case. And how does this happen? So what you do is you take a kernel, or you take a filter of size 3 by 3, or and this is, again, it depends. You can take any filters of any size. It can be 3 by 3, 5 by 5, depends. So here in this illustration, they're taking a filter of size 3 by 3, and then what they're doing is they're first putting it at this position, and then they're individually doing dot product. So they're basically doing element wise multiplication between the this 3 by 3 position of this image and the 3 by 3 kernel, and then they move it one position, and they again apply it to this position, and they do element wise multiplication, and they add all the values, and then they get this 3, and then they again put it here, and so on. And so when they're doing this, you can see eventually you'll have, so how, in terms of height, how much can you go? So you can apply 3 by 3 here, and then you can move it 1, you can apply it here, and then you can move it 1, and you can apply it here. So there will be like 3 in length corresponding to the width, and similarly there'll be 3 in width corresponding to the height, and so you'll get a 3 by 3 output. Okay, so and so this kernel that you're applying, this 3 by 3 matrix that you're applying to your image, it has some numbers in it. These numbers are actually the weights. These are actually the weights that you'll be learning through backpropagation. So in case of a simple neural network, where you had a matrix that you'll multiply to the input layer, so there are weights corresponding to this transformation. Similarly, in for convolutional neural network, the weights are in the form of kernels. So these 3 by 3 matrices that you're applying to your image, these 3 by 3 matrices have 9 values in them, and these 9 values are learned. They are learned through backpropagation. So you do not specify them. You do not say, oh, this 9 by 9 matrix should 3 by 3 matrix should be this. Instead, you learn it through backpropagation. And so here you're applying one kernel so here you have a 5 by 5 image, and you're applying one 3 by 3 kernel to it, and this is your output. and then again you can apply another kernel. So you can take another 3 by 3 kernel and apply to this, and you'll get another 3 by 3 output, and you can stack this output. So you have one 3 by 3 output, and then you if you apply another kernel, you have another 3 by 3 output, and then you apply another kernel, you have another 3 by 3 output. Say you apply 100 kernels to this same image, you will get 100 outputs of size 3 by 3. So the effective output size will be 100 by 3 by 3. So I hope that's clear. So like this is another GIF illustrating like how it's exactly working. So you apply convolution, you apply a kernel at each position, and corresponding to that you get a output. And so one thing is the kernel size need not be 3 by 3. It can be any size 4 by 4, 5 by 5. It depends. And also, so how much you're moving in each step, the delta between each step. So here the kernel is moving one at a time. Instead, you can move two at a time, you can move three at a time. That is something called stride. So here the stride is one, which means that you're moving the kernel one position at a time. If you have a stride of two, then what will be the output size? So if you have a stride of two, you first apply your 3 by 3 kernel here, and then instead of keeping it here, now you move it two places. So you will have your kernel here. So in that case, the output there will only be 2 by 2 output instead of 3 by 3. So it varies like that. So based on your kernel size, based on your stride, the output size will vary. Okay, yes. Yes, the lab is being recorded. Yes, Aditya.
So you said we can stack as many kernels and we, in the end, have 3 by 3 only. But shouldn't it be one by one when you apply the next kernel?
No. So wait. I don't mean it like that. So what I meant was, I did not mean that you apply the 3 by 3 output on this. If you apply furthermore, if you apply a 3 by 3 kernel on this, yeah, you will get one. But then if you, I'm saying you, so you applied a 3 by 3 kernel on this image, and let's apply another 3 by 3 kernel on this image again, not on the output, but on this image. So you can apply as many kernels as you want on the original image, and so you'll get that many outputs, and then you can stack the outputs to get like, so if you have apply 100 kernels, you'll get 100 by 3 by 3. If you apply 50 kernels, you'll get 50 by 3 by 3 output. Okay, that's cool. Okay. So yes, Sahil.
So the benefit here is that instead of training 5 into 5, that is 25 weights, we are training only 9 weights.
So in this case, all the 9 values in this kernel will be learnable weights. So it depends upon how many kernels you use. So if you use 10 kernels, 10 learnable kernels, then there will be 10 times 9, 90 weights that you can learn. And the difference is that in terms in fully connected layer, each of these connections have different weights, right? So like all of them have different weights. But in convolutional neural network, so when you're first applying the kernel here, there are so when you're applying the kernel here, or when you're applying the kernel here, or when you're applying the kernel here, the values of the kernel are remaining the same. So like the weights inside the kernel, the 9 values inside the kernel, they are same when you're applying to any position within the image. So in that sense, you're saving a lot of weights because you're sharing weights. The very important concept here is called sharing of weights, which means that these kernels that you're learning, when you're applying them to different positions in the image, you're not having different weights for them. You're applying the same kernel at different positions, and the weights of the kernel remain the same wherever you're applying it to the image. And so you save a lot of weights, you save a lot of parameters when you do this. Another reason is that, which I'll come to. So is there a question?
Like it's even considering the local spatial arrangement also as a factor.
Right. So yeah, that is what I was coming to. So if you take any image, let's say you have an image of a tree, or say you have an image of multiple trees, and in that case, so in real life, objects in real life are hierarchical in the sense they are built from smaller and smaller things. So if you take a look at a tree has components within it. So it'll have its bark, it'll have leaves, and so on. And these leaves, so if you look at one leaf on a tree, then the features of this, so the characteristics of this leaf will remain the same irrespective of which leaf you're looking at. So like you do not have to learn different weights or different the so basically what I'm saying is you need to have some property of your neural network which can identify that a leaf, irrespective of where it's in the image, is a leaf. So like if the image, if there was a leaf at this position, or there was a leaf at this position, or there was a leaf at this position, then you do not want to learn like separate weights for that. You want to apply a kernel at each position, so that this kernel can identify, oh, there's something here that looks like a leaf, there's something here that looks like a leaf, and then it's reusable, right? Irrespective of where a leaf is present in an image, you can use the same kernel to identify that. It's not exactly a leaf, like it's kernels identify patterns, but I'm just taking an example. uh, yeah, so that is a property called spatial invariance, which means that there is a property of convolutional neural networks called spatial invariance, which means that irrespective of where you have an object in your image, irrespective of where you have a pattern in your image, when you're applying a convolution to it, because the weights of the convolution are same wherever you're applying it, the output will be the same. And you can move around this object and you can still get a similar output because these convolutions are being applied all over the image. Yes.
When you said there will be 10 kernels, what did you mean?
There will be 10 matrices. So here you have a 3 by 3 matrix that you're applying to this image. Instead, so first you apply this 3 by 3 matrix, you get this 3 by 3 output. And let's throw away that matrix. Let's take a new matrix, a new learnable matrix that you can again apply to this image, and you'll get another 3 by 3 output, and so on. So I'm talking about, like, when I'm talking about 10 kernels, I mean 10 different 3 by 3 matrices that I'm applying to my image. And these are all different matrices. Like, so the first matrix will have a 9 weights, second matrix will have different 9 weights, third matrix will have different 9 weights. And you can think of it like maybe the first matrix is identifying a bird, the second matrix is identifying a leaf, and so on. It's not exactly objects, it's more of like patterns, but you can think of it like that. So like the first kernel, say, it's recognizing like checkered patterns, second is recognizing maybe like circles, and so on. So it will learn to do that. You are not specifying, you're not saying, oh, so this first kernel should identify, you're not explicitly saying that. Through backpropagation, when you're learning the weights, automatically these kernels will learn to identify different shapes and patterns in an image. And that is the most important property of convolutional neural networks that make them extremely applicable for visual data. Yes.
So in a way, we are creating new features.
Yeah, it's features, yes.
So kernel 1 will create, say, a subimage 1.
Yeah.
Kernel 2 will give subimage 2 and then subimage 3.
Right.
And then we will have more kernels for this layer and create another layer and finally to the out.
So you can have as many of this as one. So like, so this is a very small image. So say you're dealing with a 256 by 256 image. So applying this 3 by 3 kernel won't make it a extremely small output. It will reduce its dimensions, and then you can maybe apply again. You can apply again 3 by 3 or like a different kernel size to this output, and then again you can apply different set of kernels to this output. Eventually, the size will become smaller and smaller and smaller, and then finally maybe you can apply fully connected networks or something like that. So the most important part here is that you're saving a huge number of parameters because of this weight sharing, because you're sharing these weights and you're not like connecting. So imagine you have this 5 by 5 and then you have this 3 by 3 and you connect like every single position to every single other position. Then you'll be having a lot of redundancy, right? So in order to avoid that, so convolutions help in that regard. So I hope that's clear. So I had one more GIF that I saved of like how, okay, it's not, yeah, of how it works. So like you have a 3 by 3 kernel that you're applying here at each position in the image, and then like you get the corresponding output, and then maybe you can take this output and then you can again apply different kernels to it, and then you'll get again outputs and so on. Yeah, that's it. So like I just wanted to give a basic idea of how convolutional networks work so that it's not completely going over your head. So that's cool then. So if there are no questions, I'll start with the actual stuff for today. Cool. So we'll be using CIFAR 10, right? So Kaggle, I hope you know the website called Kaggle. It's a website where you can do machine learning competitions, and like there'll be like lots of notebooks that are available that people have already written. There are also datasets available. So we'll be using this dataset called CIFAR 10. It has 50,000, 60,000 labeled images of objects, different kinds of objects. So 10 here refers to like 10 classes, meaning like there are 10 objects belonging to 10 different classes. So there'll be like frogs and there'll be like automobiles and so on. So if you want to download the data, you can go to data and then you can click download. And before that, you'll have to log in. So so what you have to do is you can go to first. So, okay. So to use the Kaggle with your Colab notebook, you'll have to download something called a token. So you have to go to your account. You can go to, right. I think, yeah. So here there's something called an API. So you have to click create new API token and it'll download a token for you. And then what you can just do is you can just go to your collab and then just wait, let me just connect to a runtime. Okay. So what you can do is you can just upload your right. You can upload your Kaggle.json file. Okay. Here and then you can just make use of that. So you need this Kaggle.json file in order to download data to your collab, onto your collab instance. So let's see how we do that. So once you have your Kaggle.json, what you have to do is you have to install. So there's this pip package it's called Kaggle. So you have to pip install it first. So I mean, from first lab, I think you know how to install packages. So you just do pip install Kaggle. Let's mm, oh, okay. What is the problem? Oh, okay. I'm done. Okay. Uh, so and then you have to change the. I mean, this is not important. Just trying to get the data. So you're just changing the modifications of the permissions of the JSON file. Okay. So now what you can do is wait. Did I close it? Kaggle Sifatan. Okay. So if you go to data, they'll tell you exactly what to run to get the data set. So if you just copy paste this, Kaggle competitions download Sifatan. Right. So it'll download the data set to your current working directory. So it'll be just here. So you can do this for any data sets, not just CFUT, and there are like a lot of data sets available on Kaggle. So if you just want to use any data set, just go to the data section and then there'll be like either you can click download or I think it'll download as a zip file. Or you can just so if you have your Kaggle.json file set up, and then you can just directly just do Kaggle competitions download and then whatever it is. Here it's cfutton and then depending on what data set you use. Okay, so it's downloaded. So we have a zip file called cfutton.zip. So we'll unzip that first. So now you have a train.7zip, you have test.7zip, and you have train labels.csv. So the train.7zip has the train images, and test.7zip has the test images, and then train labels.csv has like a map. So like a map corresponding from the image name to like what label actually is the image. So if you have like if you say 1030.png, then what label does this image have? So does this image have a frog? and so on. That information is contained in train labels.csv. So we'll look at that later. So now you have, so wait, I'll make a directory called dataset. Call it dataset. Let's move the 7 files to dataset. And also the okay. So so now your dataset folder has your all the stuff. Okay, now let's now I'm inside the dataset folder. So I'll extract the train.7zip and test is not required right now. I'll just extract the train.7zip file. So that it's basically a zip file, but then it's a specific kind of format of zip file. So maybe you have to use the 7zip utility for extracting it. You cannot use unzip. Okay, so this will take them some time to extract. So while this is extracting, let's think about how we are going to load the data. And I'm talking about the labels. So let's actually look at the labels. I had downloaded this before somewhere. Let's see, DL lab. Yeah, right. Yes, please. So this is what train.csv has. Let me try to zoom in. And it's not working. Right. I hope this is visible. So this is what train.csv has. So you have an ID and you have a label. So this ID corresponds to the image name. So like basically 1.png will have a frog, 2.png will have a truck, 3.png will have a truck, and so on. And we have to load this information somehow. This is not readily available to us. So we'll have to open the CS file, pass this file, and just load this data so that we can use these as the ground truth labels. And so it's just basic file parsing that you can do. So let's do one thing. Let's make a function. Let's call it, and then it path to CSV file. And what this function does is it'll read the labels and it'll return it in some format, like a dictionary or something like that. So what we can do is we can open the path to CSV file. Let us read. And then also, like, we don't need the first one, because first one is just ID comma label. It's just saying, like, it's just a heading, right? So we don't need the first one. I guess we can just take from the second line onwards. And so we have loaded the lines, and so like each line will have 1 comma frog, 2 comma truck, and so on. And so what you can do is we can split it. We can split each one at the comma, and then we can put the first value as the key of the dictionary and the second value as the value of the dictionary. Yeah, it's pretty straightforward. So we can do this. Comma. And we can just make a return dictionary, which is do is we can take name, comma, labels, and tokens, and then so you take the each token. Each token means each token corresponds to this. So it'll be a string, and then you uh, remove. So I do R strip so that if there's something like passion or something like that here, you can remove that. and then you split it at the comma. So if you split it at the comma, you'll get a list, and the list will have the first element of the list will be 1, and the second element of the list will be frog. Keep in mind that these are strings. Even after splitting, one will also be a string. And then I just make a dictionary. So the dictionary, the key of the dictionary will be name, and then the corresponding value will be labels. It's just basic. Okay, so now we have to wait for this to end so that then we can actually read the CSV file. It'll just take a couple of minutes, I think. It's extracting the file. Okay, so once this is done, so like we have written a function to read the CSV file. So you can call that read CSV file, CSV labels on whatever, wherever, so or file is train labels.csv. So we'll call it on that, and this will give you the labels. Cool. I think it's done. Okay. Uh, right. So it has finished extracting. So like 50,000 files. So there are 50,000 files in the train.zip file. So 50,000 images. And so now we need the labels corresponding to these images. So we wrote a function which opens the CSV file and then gives you a dictionary with the name and the corresponding label. And so yeah, I already ran that. And then I call that function on train labels.csv. So I'll get the corresponding labels. So if you look at labels, uh, uh, okay. Why is it none? Oh, right, right. Okay. In the function, I forgot to return the dictionary. Lol. Unreturned it. So now you can see there's a dictionary, and in this dictionary, corresponding to each, so like if you do labels of 434, I mean like anything 535, and then you'll get the corresponding label, which is a dog. So it says that 535.png is a dog. So now you have the label information, and you also have extracted the data, and it's there in this train folder. Okay, but now, so the thing is, uh, this format of the label is not enough, right? So like you can't tell the model, oh, it's an airplane. You need to give it a corresponding label, like a class ID. Like last time when we had numbers from 0, 1, 2, 3, 4 up to 9, we had a corresponding class ID. So it was like 0, 1, 2, 3, 4 up to 9. So we need that kind of information. I mean, so what we'll do is we'll convert this. So we'll say truck. If it's a truck, predict 0. If it's a ship, predict 1, and so on like that. So what we'll do is we'll make a map from these names to a number from 0 to 10. I mean 0 to 9, because there are 10 labels. A number from 0 to 9 will map the names to a number. So that's pretty much straightforward. So what we'll do is we'll first get the list of all the values that are there. So how do you do that? You can just make a set. Uh, Values. These are the different labels that are there in this data set. And what we'll do is to airplane we'll assign 0, to automobile we'll assign 1, to bird we'll assign 2, and so on. so that then we have it in a numerical format. So what I'll do is I'll make a dictionary, and then I'll just write a simple for loop which will just assign values. Right, it's called values. Should I get class map now? What I've done is I've just made a simple map which maps like, so ship is 0, automobile is 1, frog is 2, and so on. So that we can use this information. So like later on when we're loading, so say we load this image, we are going to pass, say, this image to the model. So we want to know what the label is. So first we look at this dictionary. So this dictionary says that it's a cat, or it's a cat, and then you can use this dictionary which says, oh, a cat, so it's a cat will be 5. So then the target will be 5. So like the ground truth target that you'll pass through to your loss will be 5 in this case. I mean, yeah, you can make a single dictionary which combines both of these, but let's leave it for now. Okay, now let's actually make the dataset. We need a dataset class. We need a class corresponding to the dataset. So whenever you're implementing a custom dataset, you'll have to implement it as a class, and this custom dataset will need to have. So let me custom dataset. So every time you implement a custom dataset, you have to have two functions, and these functions are, there has to be a function called len. Okay, so I just realized. Okay, so it has to be underscore len. So I just put hyphens for now. Okay, that also won't work. Okay, there has to be a function called len, and there also has to be a function called get item. And what these functions will do, we have to implement is that, so the length will have to return how many files are there in the dataset, and when you call get item on with a number, you'll have to return the corresponding image. So every time you implement a custom dataset, you'll need to have at least these two functions. You can have other functions in it, but then at least you'll have to implement these two functions. Okay. So let's make a class, and let's call it cfutton. And this class will need to have two functions. One is length, and one is get item. Oh wait, what am I doing? Get item. Okay. And another important thing is that you have to inherit this. You have to inherit from a class called dataset. So let's import a few libraries first. Torch. We need OS. We'll need. I'm not sure what else we'll need. Maybe NumPy. There's this. So in torch.utils.data, there's this class called dataset. You have to import that. You also have to use data loader also at some point. So we'll import that right now. I mean, data loader. Just to load the image, we might need below image, and yeah, that's pretty much it for now, I think. Okay, so this anytime you're implementing a custom dataset, you'll have to inherit the class that you're implementing the dataset with dataset. This dataset class in torch.utils.data, you'll have to inherit from that class. And then you'll also have to compulsorily implement these two functions. You can have other functions in here, but then compulsorily you'll have to have these two functions if you want your dataset object to work. So so the length len, what should len do? So later on you'll be like dataset is equal to cfar 10, and then you'll if you at some point, if you call length of the dataset, then you want this to return the number of images that are there in the dataset. So you'll have to implement that functionality by yourself here in this function, so that whenever you're calling len on this dataset, it should return the number of images that are there in the dataset. So let's do that. So init. Okay, so I forgot to have there should be an init method as well, of course. Init method will take the path to the data, it will take path to the CSV file. What else do we need? Yeah, we need the labels. We need the class map that we made earlier. We need the what is it called? Yeah, class map. We need the class map, and if you're gonna apply any transforms, which I'll talk about earlier, we need that as well. Let's just make the attributes is data path. Okay, so you have your init method done. So these are all the information. So when I'm creating the data set, I'll have to specify where the data is, where is the CSV file, what are the labels, and so I'll need the class map. I'll need to make use of the class map if I'm going to. So when I call get item, I'll have to make use of the class map to get the corresponding labels as well. And if I'm going to apply any kind of transformations on my image, so this is fine for now. I'll talk about it later. So length. So let's implement the length now. So what should the length do? So the length should first go to data path. It should list all the files in the data path, and then it should return the length of that. Right. So how do you list? So there's this method called in OS, in this library called OS. There's a method called uh, uh, this directory, which takes in takes in a data which takes in a path to any fold directory, and it takes in any path and it lists all the elements, all the items that are there within that path, within that directory. Okay, so so you'll takes data path and you'll call os.path.list directory on it, and okay, so this has to take itself. And then so this will give you a list of all the files that are there at this path, and then you can just use call the length on that list. That will give you the how many files are there at this path will be given by this, and then you can just return that. Okay. So let's just see if this works. Like before we implement get item, let's see if it works. So we'll make a data set CFA10, and then we'll pass to it. What all do we have to pass to it? We have to pass the data part to it. So let's first see where we are at right now. The current working. So we're here. So we just have to give train, and then the path to the CSV file is train labels dot CSV. The labels is there in labels. I think it's in labels. Right, it's in labels. I mean, it's not important right now. So like, but then we'll pass it. Transform is none. Okay. Wait, what? Oh, okay. I think it's OS.list directory. Right, it's OS.list directory. Lol. Okay. Right. So now when I call length of the dataset, I made a dataset object by calling cfa10. I made a dataset object, and now I call length on the dataset. So I got 50,000 because that's how we've implemented it. We've implemented it so that it looks at this directory, it lists the items in the directory and just returns the length of that. So we'll give you how many files are there this path. Basically, it's a basic implementation. Okay, so now you have implemented the length. Now you have to implement the get item. So what does the get item do? The get item takes in an index, and it will return the image corresponding to this index. So first, what do we have to do? So we have an index. So index say so if you say data set of 10, so what do we have to do? So we have to take this index, which is 10, and then we have to print the corresponding image. So the data set of 10 will be an image, data set of 11 will be another image, and so on. And so we have to open an image each time. So whenever you're saying get item, you have to open an image each for each of this, right? So to get the image, we have to first open it. So for that, we use the library called Pillar. It has this module called image. And so how we can open it is you can just do image dot open, and then you have to specify the file name. So in this case, the file name will be what index.png. So in this case, it won't be index.png. It will be index plus 1.png because index starts from 0. So dataset, it starts with 0, dataset of 0 to dataset of something. But then the actual file names are starting at 1. So if you look at train inside the train folder, it will be from 1.png, 2.png to up to 50,000.png. and it's not starting from 0.png. So corresponding to that, you'll also have to add 1 to your index so that you also start at 1.png instead of 0.png. So right, so you take your data path, and it'll just right, and then right. So what I've done is I've taken the data path and I've joined this data path with string index plus 1.png means, so index plus 1, say we supply the index as 3, so index plus 1 will be 4, and we'll take 4.png, and so what this does is os.path.join means it will join the data path with the image, so it'll become train slash 4.png. Wait, I'll just show that so that it's clear what exactly this does. So your data path is train, and you do os.path.join data path, let's say 4.png. So this will give you train slash 4.png. So it will give you a path to the exact file. So here what it does is just add the slash, but yeah, it's a function that you can use later on when you're dealing with like complex paths and stuff. It's better not to actually just put in the slash by yourself, but rather let it call this function on it. Okay, so now you have the path to the PNG file, and then you call image.open on this path, and it'll open the image for you, and then you can store it in some variable. And now, so this image that you've opened, it is in the form of a pillow image object. It's an a pillow image. Now you have to convert it into a tensor because your PyTorch only deals with PyTorch tensors. So you have to convert the image that you have loaded into a PyTorch tensor of whatever dimensions. So how do you do that? So for that you'll need torch vision transforms. So we used this last time as well, so it shouldn't be transforms dots. It's a transform called to tensor, and we can call that on image, and you'll get the image tensor. Okay, so you have loaded the image tensor, so that's fine. The image part of the data is done. Now you don't just need the image, you also need the corresponding label. And how do you get the label? Again, you can use so you have something for that you've implemented something called as class map, so you can use that. So first we'll get the label. So labels and then you can get the class ID corresponding to this label using the class map that you made earlier. And then you can just return your image tensor and the class ID. Okay, let's see if it works. Right. So when I call dataset of 0, what it does is it returns 1.png basically. It's returning 1.png. So I'm getting a tuple, and the first element of the tuple is the image tensor, this thing, and the second element of the tuple is the class ID. So it says that this 1.png has the class 2. It has an object which belongs to the class 2, and which is what is class 2. So from our class map, we know that class 2 is frog. So the 1.png has a frog in it. Okay, so this is how you implement a custom data set. And now you have a custom data set, you have to implement something called a data loader. So what the data loader does is it will take this data set and then it will load data in the form of batches. So you do not want to load an image one by one. If you remember, we used to pass batches at a time through your model. Also, you might want to shuffle your data, and all this stuff is implemented in here, like implicitly in something called a data loader. And for making a data loader, we use torch.utils.data.data loader. So let's make a data loader. So we are using this class from torch.utils.data called data loader. And this data loader, so let's look at the PyTorch documentation. torch dot utils dot data data loader. Yes. So torch.utils.data.data loader. So the first thing that it takes is a data set from which to load the data. So let's give that data set, which we have already made now, which we have instantiated now. So data set is of type C for 10. And batch size. So we can specify a batch size, let's say 10. I mean, okay, 10. Shuffle. If you want to shuffle your data, you can give shuffle. Right, that's pretty much it that we need right now. There are a lot of other things that you can have. I don't think we need anything else right now. So let's do that. Okay. So now when I so every time the data loader is called, it will return a batch of images. So here you can see it has returned a batch of images. So it returned 10 images and the corresponding 10 labels. So first image has class ID 5, second image has class ID 6, and so on. So data loader basically, it's, I mean, from the name, it should be clear that it loads data. And how does this load data? It makes use of the data set that you created, and it will give you the data. What format does it give you the data? It gives you the data in the form of batches, and you can specify the batch size. If you want to shuffle the data, you can do that as well. So every time in every iteration, so every epoch, in every epoch there will be a different order of batches. Instead of having the same set of batches, there'll be a different ordering of the batches, and there'll also be different images in the batches, of course. Okay, so you have a data loader now, and so okay, maybe you can look at, if you want to visualize what is actually there in the, if it's actually giving an image. Let's create a simple function which takes in a tensor, and we'll just visualize the image for you. And for this we'll need matplotlib. All this does is and then let's just right, data set. Right, so you can see it's a frog. I mean, it's a 32 by 32 image, so you can't expect high definition. But you can tell it's the image of a dog, image of a frog. So dataset of 0 will give you a tuple which has the image and the label, and I took the first element of that, which is the image tensor, and then I passed it to visualize image, which is just a simple function that I wrote, which just converts the tensor back into a PIL image, and then it just shows the image. And so you can tell. So this is how you can tell that your data set is working. And again, so if you want to check if a data loader is working, you can assign this to data item. Say call this data item, and so data item will so data item. Let's look at the length of data item. So the first element corresponds to the images, second element corresponds to the labels. So data item of 0 will be the list of all the images. So because our batch size is 10, it will be a list of 10 images, and 0th one of this will be the 0th image, and we can pass this to visualize image. Right. It's a dog. I think it's a dog. I mean, I can't really tell, but I think it's a dog. Right. So our data loader is also working. Now, what do we have to do? So another thing that we have to do is, so if you remember, we have to normalize our data before we pass it to a neural network. We usually normalize our data. So we have to normalize our data. Plus, if you want to apply any kind of augmentations, so what are augmentations? So what if you want to apply some kind of like some kind of transformations to this image? What if you want to rotate this image by an angle? You want to rotate this image. you want to crop some parts of this image, or you want to I mean, there are many transformations. So if you go to torch vision, so it's in torch vision. Torch vision Torch vision has a lot of transforms, so you can see all these transforms here, and this will also be asked in the quiz today. So transforms, so there are different types of transforms that you can use. There's something called center crop. It's grayscale, so if you apply grayscale, then it will make your image grayscale. You can have so you can randomly rotate your image by certain degrees with some probability. You can resize your image. All these kind of, there are different kinds of, you can apply Gaussian blur. There are different kind of transformations that you can apply to your image. And why do you need to do this? So like this is a very useful thing to do when you're training a neural network. Sometimes you're if I mean, it's a way of improving the performance of your neural network. If you're like doing some kind of randomness to your image, and then you're passing it through a neural network, and then your neural network still learns to look past these perturbations. And so like if I make this image grayscale, then your neural network still has to understand that there's a dog here. If I rotate this by like certain degrees, then it does not become a cat, it's still a dog. So like your neural network has to learn that it's still a dog irrespective of whatever kind of transformations that I apply to this image. And so applying these kind of transformations before you pass it to your model while training is a good idea. Usually it's a good idea. So what you can do is have you can apply these different transformations, and for that you can make use of transforms that are already, you can implement your own transforms, or you can make use of these like a long list of transforms that are available in torch vision. So let's declare a transform. So let's say or transform, let's say it uh, normalized transform. And let's look at the documentation for normalize so that we don't mess up. Right. To normalize, it takes in a tensor image, and then it normalizes the tensor image with some mean and with some standard deviation, right? And this transform does not support PIL image, so we have to pass it as a tensor. So let's declare. So now we have to specify what is the mean and the standard deviation that we want to normalize this image to. And usually, when we're dealing with ImageNet, I mean not ImageNet, when you're dealing with CIFAR 10 or any kind of dataset, what we usually do is we'll take the mean and the standard deviation of the dataset of the images, and then we'll normalize each image with that. So I hope I'm clear. Like what we're doing is we take the entire dataset, we take all the images. So here in this case 50,000, or in case of ImageNet, we take all the millions of images, and then we take the mean and standard deviation of all the images together. And then what we do is we take each image and then we normalize it with that. So like we normalize, use that mean and standard deviation, and then we apply that normalization to each image. Uh, so so typically for computation, any kind of computation model that you make, I mean it's a standard practice to normalize your images with the mean and standard deviation of ImageNet, because usually you'll use ImageNet pre-trained weights. And so it's a standard practice. Like you can choose to do it, you can choose not to, but it's a standard practice to normalize your data with the mean and standard deviation of the ImageNet data set. So these are actually the weights. So in this example that they've given here, these are actually the weights of mean and standard deviation of ImageNet. So let's just copy paste that here. And when in your data set, you have this transform parameter that you're passing to your data set. So what I can do is you can just so if you're passing transform, then just apply that transform to your image. Otherwise, just return as it is. So if there is a transform, if you're specifying a transform, then apply the transform to your image and return it. Instead of returning the image itself, first apply the transform to image and then return it. And so now if I make a data set, and then now if I take data set of 0 and visualize it, right? So like this is, so the image has been normalized, or I hope so. Wait, let me see. So I made a transform and then I passed the transform. Okay, I did not pass the transform, right? I did not pass the transform. So you have to pass the transform here. Transform is equal to transform. Right. And now if you visualize the image, you can see it won't make sense because now we have normalized the image with mean and standard deviation of the entire data set. So now this will only show like how much each pixel is differing from this mean and standard deviation. So you can't actually visualize what's happening, but then now when you pass it through to your model, the model will might be able to better like distinguish between a frog and a dog, and that is the goal, right? Okay, so and also you can also compose transformations. So you can have apply transformations one after the other. For that, you can use transforms dot compose, and to this you can just pass a list of different. You can pass a list of transformations that you want to apply. You can just have a list of. It's, so say you want to randomly flip your image, but horizontally. So you can have a transform for that. So there's this transform called random horizontal flip. What is this does is it'll randomly just flip your image. So initially you had a dog image like this, so it'll just flip it horizontally, like mirror it. Basically, it'll mirror it, but then randomly apply it. It won't do it all the time. It will randomly mirror it. That is also a kind of data augmentation that you can use. That is might be useful. And then so now you have composed to transformation. So first it will normalize, and then it will randomly flip it. It might not flip it all the time. It will randomly flip the image, and then it will pass it to a model. Okay, um, so now what all have we done? We have made a custom data set. We have made a data loader which takes this data set and it will passes batch by batch images. It will shuffle it also. We have also specified transformations. So these transformations will be applied to your image before the data loader gives it to you. What will it do? It will take these transforms. It will apply it to your each image, and then it will give that data to you. Okay, so now what do we need? We have a data set, we have a data loader, we need a actual model we need. So I'm not going to write a whole model now. We'll just use the model from last time that we wrote. The CNN classifier is pretty good enough for now for illustration purposes. Let's see. Collab. We just copy paste that because there's nothing else that we actually need. I mean, there's nothing new that we have to implement. Let's see. Right. CNN classifier. So right. So this is the classifier that we implemented last time, but then we have to make slight changes to it because last time we were passing 1 by 28 by 28 images to it, but this time we are passing 3 by 32 by 32 images to it. So accordingly we'll have to make certain changes to the model. Okay, so for to do that, first we have to know how the shape of a feature map changes after we apply convolutions to it. So okay, let's look at that. Wait, I'll just actually write down the formula here so that. So say you have an image of size 32 by 32, 32 by 32 image, 3 by 32 by 32, and to this you apply a kernel of size 3 by 3. So like we saw earlier. And so what will be the size of the output? The size of the output. So to do that, we have to use a formula. I mean, it's logic, but then there's a formula that you can derive for it, and this formula is so dimensions of the output. Is it not letting me? Okay, so this is a code cell. That's why. Log text. the dimensions of the output. Uh, okay. So okay, wait, let me use. I hope this is visible first of all. So this is the formula that you can use to get the what are the output dimensions after you apply kernel. So say you have a 32 by 32 image. So the input dimension will be 32. So D in will be 32. And let's ignore P for now. It's 0 here. Let's ignore that as is. And then you have a kernel K of size 3. So what is 32 minus 3? 32 minus 3 is 29. And say your stride is 1, which means you're moving your kernel one at a time. So that is here. S is stride. So you're moving a kernel one at a time. So 32 minus 3 is 29. And then you add 1, it will be 30. So yeah, after if you apply a kernel of size 3 by 3 with stride 1, then after you apply this convolution, the output will be of size 30. Right after you, so it will be what? It will be a 30 by 30 image, 30 by 30 output, and depending upon how many kernels you have. So if you apply 10 kernels, like I was telling earlier, one kernel you can apply two kernels, and so on. So depending upon you apply 10 kernels, then the output will be of size 10 by 30 by 30. Is this clear? Like, is there any questions regarding this? Because it's very important. Because otherwise, I can't tell how I'm changing the classifier. Okay. What is? Yeah. What is? Oh yeah, I'm coming to that. Um, so P. So this much is clear, right? So this much is clear. So like this is formula that you can use, and now you have to. There's something called P. So P is padding. Padding. So what is padding? Padding means you put empty pixels around your image. So what does that mean? So wait, I'll just actually Google it. Uh, right. So say you have an image. So say the thing in blue. The thing in blue is your image, and you're applying convolutions to it. And the thing is, when you're applying convolutions, your image size will decrease. So to control how fast or like how much the size of your image is decreasing, what you can do is you can put empty pixels around your image. So like I can just these are just blank pixels 0 0 0 0 0 0. There's no information in it. You can put blank pixels around it so that you after you apply your convolutions after you apply your convolution layer to it, the image won't be that small. Like it'll be one size bigger, right? So if you have one square pixels around the entire image, then your padding will be 1. In this case, padding is 2, which means there are 2 pixels around your entire image. It's just empty pixels. That's all it means. Is that clear? Like it's pretty simple. These are just zeros. So instead of having a 1, 2, 3, 4, 5, 5 by 5 image, now you will have a 1, 2, 9 by 9 image, just because you added empty pixels around it. There's no information in this pixels. It's all zero. It's black around it, but you're just using it so that your output dimensions are bigger. Is that clear? And that is what the P here means. Because like if you add one pixel around your image, if P is equal to 1, then P is added like on either sides of the image you're adding 1 pixel. So that's why there's a 2 times P, right? So let's take another like random example. So again, say you have a 100 by 100 image. Say you have an image of size 3 by 100 by 100. This is a 100 by 100 RGB image, and to this you apply a kernel of size 5. Okay, and say the uh, I mean, let's apply a kernel of size 6 so that it's easy to divide 6 by 6. And then with stride, let's say the stride is 2 this time. So instead of moving one box at a time, you move the kernel 2 boxes at a time. You apply with cursory and say that there is a padding P of 2. Let's say 1. Let's keep it 1 for now. this is padding of 1. So like then what will be the output dimensions? So you have to use this formula. D out is what? D out is D in plus 2 times P minus K. So D in is what? 100 plus 2 times padding, which is 1, minus the kernel size, which is 6, divide this by 2, and then floor it. So these like half square brackets mean the floor operation, which means that if there's any decimal places, just ignore that. And then you add 1 to it. So what is this? 100 plus 2 is 102, minus 6 is 98. Wait, what am I saying? 96. And then you divide that by 2. 96 by 2 is what? 46. No, 48. 48. And then you add 1 to it. So 49. 49. So your output dimension will be what? 49 by 49. And then depending upon how many kernels you're using. So if you apply 32 kernels, then it will be 32 by 49 by 49 will be the output dimension. Is that clear? Like I hope it's clear. If it's not, please do ask, because we're going to use this information right now. Okay, so in our classifier, first we are going to apply a convolution. Okay, so another thing that I have to mention, so there's another kind of layer called a spooling layer. So what the spooling layer does is it's another. So we saw convolution layers, how convolution layers work. There are pooling layers. What pooling layer does is it's basically used to reduce the dimensions of uh, of your feature map. So if you have a 4x4 feature map and you want to convert it to a 2x2 feature map, but you don't want to do any learning here, so you do not want to apply any neural network layers there, but you just want to reduce the you basically, you can think it of as downscaling. So what you can do is you can use something called a pooling, and a specific kind of pooling is called math pooling. So what math pooling does is it takes a kernel and then it applies. So it looks as the, so say you apply a 2x2 kernel here. There's no learnable parameters to the kernel. It's like a window. So let's say we take the first 4 numbers, and what math pooling does is it just returns the largest number out of that. So if you look at the first 4 numbers, it's 7, 3, 7, and 8. What is the largest number here? It's 8. So that's the output. Then you move it. So you can move it 1 at a time, or you can move it 2 at a time. Here the stride is 2. So you can see right after this, it did not take this. Instead of that, it took the square, 2 squares after that. So this square. 5, 2, 1 sits. In 5, 2, 1 sits, what is the greatest element? It sits. And then it took this 4, 9, 0, 8. The greatest element is 9. And then 3, 9, 5, 4. The greatest element is 9. So it downscaled all this much information it had. But then I do not want all of this information. I'm going to downscale. I'm just going to selectively take information from this. What information am I going to take this from this? The largest value that's present in these four squares. I'm going to take that and I'm going to make a new output. So the output size of this is 2x2, right? So it's half the dimensions of this. This is 4x4 to start with, and after applying math pooling, the output is 2x2. So you have halved your information, right? And so what is this kernel size here? Kernel size here is 2. What is the stride here? The stride here is 2. You can see in the specific example, the kernel size is 2 and stride is 2. So the general rule is when you apply kernel size of 2 and stride 2, your dimensions will halve. That's just a general principle. If you're applying a kernel of size 2 and you're also doing stride 2, then your output will be halved. So anytime you want to halve your output, just apply kernel 2 and stride 2. And the thing to note here is you're not doing any kind of element based multiplication, right? There are no learnable weights here. Like there's no kernel. The kernel does not have any weights here. It's just like a window. You're looking at the first 4 and then you're looking at the next 4 and so on. There's no actual weights here. You do not have to learn any weights to do maths pooling, because you're just taking the maths value, right? In order to just take the maths value, you do not need any weights. So maths pooling is a layer that does not have any learnable parameters. I hope that's clear. There are the kind of pooling as well. This average pooling. In average pooling, what you do is instead of taking the maths value, you take the average of the 4 values. And there's different kinds of pooling that you can do. But typically, people use maths pooling in convolutional networks. Okay, so that's what we did last time as well. Last time I used that, but then I didn't mention it. So last time maths pool 2D we used with a kernel size of 2 and stride of 2. So what happens is you're basically halving your kernel size. Okay, so now let's modify this. Let's modify this convolutional neural network that we built last time so that it works with our 32 by 32 image. Okay, so first what are you doing? You're taking your image and you're passing a con1 to it. So con1 is conv2d, which takes in something which has 3 channels. So this time we have 3 channels. Last time we had an RGB image, so it did not matter how many channels we had. But this time, so last time only 1 channel was there. So this time we have 3 channels corresponding to R, G, and D. Right. So we apply a 3x3 convolution, with the kernel size of 5 and a stride of 1. Okay, and after we do this, we can calculate what will be the dimensions of the output. What will be the dimensions of the output? The dimensions of the output will be input size, which is 32, plus 2 times padding. 2 times, there's no padding here, so it's 0, minus the kernel size. What is the kernel size? It's 5, divided by the stride, which is 1, and then you have to add 1 to it. You remember the formula, that is that input size plus 2 into padding. Padding is 0 here, minus kernel size is 5, divided by stride is 1, and then we add 1 to it. So what is 32 minus 5 is 27. 27 by 1 is 27, plus 1 is 28. So the output size will be, it will go from 32 to 28. Is that clear? Like, is there any doubt? Yes.
Could you please explain that formula again?
Right.
It was a bit confusing.
Okay. So you want me to explain the formula, or like specifically for this one?
No, the formula only.
Okay. So are you asking how this formula came out to be?
Yes.
So it's, I mean, it's not a formula that you derive, right? It's just you deduce that this is a formula basically. So I mean, in the earlier case we saw, I mean, this formula works, right? Like, so you take in an input image, which is of size 32, and then you can see, and then you apply padding to it. So imagine you apply a pixel of padding, and if what happens is that a pixel comes on either side, right? When you're applying padding. In that image that I showed earlier, do I have a GIF for that?
What is DN?
DN is the input dimension. So in this case, when you're passing an input,
D is the dimension of the input.
you're right. DIN is the dimension of the input.
So 32 by 32 image. So
The dimension of input will be 32.
Okay,
And K will be the kernel size, which is 5. That we are using here is 5.
P is the padding.
P is the padding, which we are not using here, so it's 0. Stride is what? Stride is 1. Stride is 1 because we have specified stride to be 1. And when you have all this information, you can use this formula to calculate what will be the output of the dimension. I mean, it's logical. Like, you have to derive this formula using logic. It's not like there's no mathematical derivation for it. This is like empirical, right? So like, when you have these attributes, then your output dimension will be this. Like, you can derive this just basically just look at different input sizes and different strides, and then you can derive this formula using logic. It's pretty easy. Okay. So is it clear how you got 28 from this? Because you had an input size of 32, you applied a kernel of size 5 with stride 1, and there's no padding here, and so your 32 dimensional input will now become 28 dimensional. So basically, what's happening? What is happening is your 33 by 32 by 32 image is becoming 28 by 28. And how many kernels are we using? We're using 10 kernels. We're using 10 kernels, so it'll be 10 by 28 by 28. Okay, and then what do you do? And then you apply pooling. What pooling are we doing? We are using math pooling with kernel size of 2 and stride of 2. And because we're using kernel size of 2 and stride of 2, what did I say earlier? It will halve your spatial dimension. So it will become 10 by 14 by 14. It'll just halve the input dimensions. It's 28 by 28. It will become 14 by 14. And now you apply. Another convolution. You apply a convolution again. So now you have a 10 by 14 by 14 input, and you apply a convolution again. What is the kernel size? Is 5. Stride is 1. So now what will it be? So you have 14 minus plus 2 into padding, but then padding is not there. Minus kernel size is 5, divided by stride is 1, plus 1. So 14 minus 5 plus 1 is what? 10. So right. So it'll become 10 by 10. And then how many kernels are you using? You're using 10 kernels. So it'll become 10 by 10 by 10. And then you apply pooling. And when you apply pooling, what will happen? Your spatial dimensions will halve. So it'll become 10 by 5 by 5. Okay. After you have this much, what will you do? Let's say last time what we did was we flattened it. And so this time we have 5 by 5. So this 10 by 5 by 5 map feature that you get, you take that and you flatten it into a single vector, because now you're going to pass it through a fully connected network. And so for fully connected networks, you cannot pass 2D maps to it. You have to make it 1D, which means you have to flatten it out. And you'll flatten it out. So you'll make it 5 by 5 by 10. because you have 5 by 5 by 10. So you flatten it out to 5 by 5 by 10, and then you pass it to a fully connected network. And now the fully connected network takes in 5. I'm sorry, 5 by 5 by 10, and then it gives you out 100, and then it takes 100 and it gives you a 10. So finally you need the output size to be 10. Like last time also, this time also, the number of classes is 10. So the output size of the fully connected 2 should be 10. I think that's all the changes that we have to make. Okay. Is there any doubt here as to how I made these changes? Like, so I changed the convolutions so that finally, what do I need? Finally, I need the output should be of size 10. After I do apply n number of convolutions, my output should be of size 10, and so each of these layers should be compatible with each other. So first I change it to 28, and then 14, and then 10, and then 5, and finally, before I'm passing it to a fully connected network, the fully connected network has to, the input to the fully connected network should be 5 by 5 by 10, and it has 100 hidden layers, and then 100 hidden units to 10. 10 is my final output size. Should be pretty clear, I think. Uh, I can't hear you, Prathanav. Can you just speak a bit louder?
The step where you're flattening the image,
Right.
and you parameterize the dimensions because you have hard coded 5.
Yeah, you can do that. Right, you can do that. I mean, there are no parameters, right? You're just changing the view of data. Like you're just changing 3 by, I mean, not 3, 10 by 5 by 5 matrix, I mean, tensor that you have. You're just changing it so that now it's, I mean, the actual data in it is not changing, right? You're just changing the dimensions of the layer, right? I mean, yeah, you can do that. Uh, Okay, so now you have a model. So like last time, you'll instantiate it. You'll say CNN classifier, and then you'll load it onto your GPU. Okay, so now your model is hopefully on the GPU. Okay, there's no. I think. Wait, let me just look at model then. I mean, yeah, we'll see. Okay, so now you have your model on hopefully on the GPU, and now you can pass data to it, and then uh, you can pass your data to it, and then you can train your model. So now you have a data set, you have a data loader, you have your model. What else do you need? You need an optimizer, you need a loss, right? These are the two more things that you need before you can train your model. Optimizer also, you can make a custom optimizer, but then I don't recommend it because the optimizers that is implemented in Torch are actually pretty, I mean, its implementations are pretty efficient. So if you implement it yourself, it might not work at any point. If you have to implement a custom optimizer, you can do that. There is the option to do that. But then loss, you'll have to implement your own custom loss at some point. So let's see how we can do that. So last time, so in classification, the loss that he uses cross entropy loss. So last time, what we used torch dot and dot cross entropy, I think we used at so it's inbuilt to PyTorch. You can use that. But this time, what we'll do is we'll actually implement our cross entropy loss. So I'll make a I'll make a class called cross entropy loss. Uh, so I mean, typically, I mean, you can implement it as a function as well, but in other losses, I mean, in this case, there's no state, but in other losses, in case you have to have some kind of state, you can do that. So I will call my loss function with so outputs and targets. So like last time, if you look at the so last time we directly used an dot cross entropy loss that's available in PyTorch. And to the loss, what are we passing? To the loss, we're passing outputs, and we are passing targets to the loss. And implicitly, the loss is it's calculating cross entropy loss inside, and it's returning the cross entropy loss to you. And it's implemented in PyTorch. But this time, what we're going to do is we're going to implement cross entropy loss, so that you can then see how you can implement any kind of loss in the future. Um Okay, so let's just keep it here. We'll implement the cross entropy laws. Let's just keep this for now. Let's copy paste the training loop so that you have an idea. I don't think it's a good idea to copy paste it. I'll just keep it on the side and I'll rewrite it. I think that's a better idea. Okay, so let's say we are going to train for 10 epochs, and we also want to keep track of the loss at each epoch. So again, we'll have a list for that. Let's not look at accuracies right now. You know how that works. You can add it yourself. Like the notebook is there, so you can always refer to it. Let's just look at loss for now, so that it's not complicated. And for epoch in range number of epochs, you want to train your model for each epoch. And for that, first I set my epoch loss to 0, and then I set my model to train mode. Now here, what did you do? Here you had explicitly calculated how many batches are there in each epoch, and then you had iterated. You had used a for loop to explicitly iterate through each batch. Here you don't have to do that because now you have a data loader, right? You have made a data loader, so you can just use that data loader. You can just say for batch in data loader, and so this will automatically, the data loader will automatically give you batch by batch. So and it will stop giving you batches when it's done. So you do not have to explicitly calculate how many batches are there in your data set and stuff like that. Based on the batch size, your data loader will automatically calculate how many batches are there, and it'll also determine what batches they are, and then it'll give you those batches one by one. And so if you want to also have a batch number, you can just add an enumerate here. So you have, like, you can say batch 0, batch 1, and so on. Okay, and so you have to set your optimizer 0 grad like last time. And then last we had input, output, and targets. So this time also we need, we haven't declared an optimizer yet. Lol. It's same as last time. Optimizer is optim.sgd works for us. You have to import that though from torch. Import. What is torch.optimize? I do not remember. Yeah, torch.optim, right? Torch.optimize. Cool. Okay, so now you have an optimizer. You make the gradient 0 so that so you have to do this every time, and then what do you have to do? So now you have your batch, and what does your batch have? Your batch has two elements. First element, what is the first element of batch? First element of batch is the list of images. Second element of the batch is a list of class IDs. That's how you made your data set, right? And that's how your data loader works. So batch of 0. What is batch of 0? Batch of 0 will be your image inputs, right? And you want to load these images to your GPU, so you do .CUDA. And your targets, what are your targets? Your targets are class IDs, so it will be 1 2 3 4 up to 9. I mean 0 1 2 3 up to 9. So that is your batch of 1 will be your class IDs, and then you can so first what I'll do is I'll make it a tensor, so right now it'll be a list when I load this, but then I'll make it a tensor, and then I'll also load it to the GPU. So now you have your input, and you also have your targets on GPU, and then you can pass your inputs through your model, and you'll get your output. And like last time you can calculate loss, right? So your loss will be, I mean, let's not call it loss, let's call it batch loss. Batch loss will be what? Batch loss will be, you pass your outputs and your targets to your loss function. I mean, last time it was n dot cross entropy. This time we are going to implement it. It's called image targets here. Image targets. And then you do loss dot backward like last time. And then you do a step of optimizer like last time. There's nothing different here. Like it's all same. You calculate the batch loss. You do batch loss dot backward, so it'll calculate all the gradients, and then you'll do dot step, which will calculate which will do a step of optimization. And then what do you have to do? Then you'll also add it to your epoch loss, so then you can track your total loss for each epoch. Right? And after each epoch, you can append the loss to your losses list. Each epoch, I think it's not appending. Pretty much it. We are not doing evaluation and all now. Already know how to do that, and then we can just print the loss. We don't need all of this train accuracy, train validation. Okay. So now you have your basic training script. So basic stuff that you need is there. You have you're doing your optimization. You're calculating your loss, and so now all that we have to do is we have to implement the loss. So I hope you remember what the outputs and the targets look like. The outputs. What are the outputs? The outputs will be is a tensor of size 10. So corresponding to each image, there will be a tensor of size 10, and each of the 10 numbers correspond to a score corresponding to each of the classes. So corresponding to class 0, there will be a score. Corresponding class 1, there will be a score, and so on. And then image targets tells you what is the actual ground truth class ID of the ground truth class ID of the images that you're passing to the model, right? Okay, so now let's implement the cross entropy loss ourselves, so that we explicitly calculate the cross entropy here inside this. So how does cross entropy work? So let's first look at the documentation so that we do not mess it up. Cross entropy. Okay, wait, what? I think. Oh, okay. So I'm looking at documentations for torch vision. That's why cross entropy. Right. So to the cross entropy function, what do we pass? The input is expected to contain raw and normalized scores for each class. So there will be a tensor of size 10 that we are passing, which is the output of the model, and that is expected to contain raw and normalized scores. And the input has to be a tensor of size c. So c here refers to number of classes. So in our case, it's 10. So it's supposed to be a tensor of size 10. But because we are also doing batches, it'll be batch comma c. So there'll be also batch size comma c. So in case our batch size is 10, it'll be 10 comma c, 10 comma 10. So we'll pass to the loss 10 comma 10 sized input, and we also have the corresponding targets. The target that this criterion expects should contain either the class indices. So the class indices in range 0 to c, which means the corresponding target. So that is how we have declared the targets, right? So when corresponding to an image, we'll get the class ID which says, oh, this is an image of type 0. This is an image with class ID 1. This is an image with class ID 2, and so on. So that's how we've implemented it. So it's correct. Okay. So this cross entropy loss takes in outputs and it takes in targets and then it calculates the cross entropy loss. So what is the formula for cross entropy loss? So let's look at that as well. Cross entropy formula. Oh yeah, this is it. So okay, it's not right. So you have your outputs, you have your unnormalized scores, 10 unnormalized scores, and you first internally what happens is it first passes through a softmax. I don't know if Sir has taught you what a softmax is. I think he might have. So you pass it through a softmax, and so you convert these unnormalized scores into probabilities. So instead of having 10 unnormalized scores, you'll instead have 10 probabilities which correspond to each of the classes. So the first probability will correspond to the first class, second probability will correspond to the second class, and so on for 10 classes. that is what happens when you apply softmax. And then the cross entropy loss formula is you first take a log of each of these 10 values and then you multiply it with the corresponding targets and then you add it up. And then there's also a negative sign. This is a formula of cross entropy loss. I mean, this is not a PyTorch thing. It's a deep learning thing. Like it's something. This is the formula of cross entropy loss. So now we're going to implement this cross entropy loss. So we have our outputs. We have our targets. And what will be the shape of outputs? The shape of outputs will be what? Batch size by 10, right? And what will be the shape of our targets? The shape of our targets will be 10. It will be of size 10 because no, it will be of size batch size. What am I saying? Yeah, it's of size batch size because corresponding to each image in the batch, there will be a corresponding label that is in targets. And first, what I'll do is I'll apply so number of examples. How many are there? That is, you can get that from targets to shape. And batch size is the first dimension of outputs. I mean, it's the same thing here in this case, so it's fine. Right. Yes.
For this
It's the same.
target, isn't it usually the one hot encoding?
Yes.
But for our
Yes.
code, the target is a 0 to 10
Right.
numbers, right?
I mean, so we can adjust our laws accordingly, right? We are the ones who are writing the laws. So, I understand what you're saying. So in our case, so say we are passing 10 images. We are passing 10 images through a model. We are passing 10 images through a model. And corresponding to these 10 images, you'll get a single value. You'll get the targets are a single number. So it will be like a tensor. So it says like 0, 1, 2, 4. I don't know, like 1, 2, 5, and so on. So there'll be 10 values like this, right? This is what you're saying. This is how our targets are right now. But then when you're applying cross entropy loss, this has to be in theory. It has to be actually in place of 0, it has to be a tensor of size 10. So it has to be like 1 comma 0 comma 0 comma 0 comma 0 comma, or 1 it has to be 0 comma 1 comma 0 comma 0 comma and so on. This is what you're saying, right?
Yeah, yeah. Right.
So instead of having, so you cannot just hit 0, right? You have to, so like cross entropy loss, when you're applying cross entropy loss, the output is of size 10, and so your targets will also have to be of size 10, but you do not have your targets of size 10. Your targets is of size 1, because for corresponding to each of your image, you have one single number, right? You have one number which says that, okay, this image contains a class ID of 7. But then when you're applying cross entropy loss, you need a corresponding target of size 10. So how do you make the target? So if your image has a class ID of 7, then what you do is you make a tensor 0 comma 0 comma 0 comma 0 comma 0 comma 0 1 0 1 2 3 4 5 6, and just in the 7th position it will be 1 8 9. And then similarly, if you have so corresponding to 5, what you'll do is you'll 0 1 2 3 4 5, you'll just make 5 1. And so this will be you can have the targets in this format, or you can have the targets in this format that we have right now. So right now our targets are just a single dimensional tensor, and the single dimensional tensor corresponds to the class IDs. But when you're applying cross entropy loss, in theory, when you're applying cross entropy loss, your targets has to be in this format. It has to be in this format called, that Noah said, it has to be in a format called one hot encoding, which means that corresponding to corresponding to which position class it is, only at that position you have 1, and at all other positions you have 0. This is logical, right? This is logical. So uh, if you say the ground truth, so say you have an image of a frog, and frog corresponds to class index of 2, and so your model, in theory, your model should predict 2 with 100% probability. It should predict 2 with probability of 1. So the ground truth should be 1 at position 2 and it should be 0 everywhere else. Your model will be predicting what will be the output of your model. The output of your model will be again something like 0 0.01, 0 0.04, 0 0.5, 0 0.02, and so on. It will be probabilities. After you apply softmax, the output of your model will be of size 10 and it will be probabilities corresponding to each class. And so the ground truth should also be probabilities corresponding to each class. But then the ground truth, there's the probability is 1 for one class, it will be 0 elsewhere because there is only one class in your object, in your image, right? And all the others should be 0. And this format is called one hot encoding. This format is called one hot encoding. But then that is not how we have our data right now. We have the data such that we just have the class ID. So corresponding to the first image, we are saying it's 0. We are not saying it's 0. We are not saying it's 1 comma 0 comma 0 comma 0 comma 0 comma and so on. And so we'll write the laws such that it makes use of this instead of, I mean, when we're implementing, we can do it however we want it, right? In theory, yes. In mathematically, it has to be in one hot encoding, but then you can do a mathematically equivalent thing using just this. So what we'll first do is so if you look at the formula for cross entropy loss, you're first applying softmax and then you're applying this log. So you're applying a log to a softmax. And for this, there's a combined function called log softmax in torch.functional and in .functional. There's a combined function called log softmax. So what this does is it takes in softmax. It first does softmax and then it applies the log. So that single function is there in torch and .functional and it's called log softmax. And you apply this to the outputs along dimension 1 because the first dimension is batch size and you do not want to apply it along that dimension. You want to apply it along the dimension of the output actual data. And once you have done that, what you have to do is you have to element wise multiply your modified output with the targets. And in theory, the target should be in one hot encoding size, this 0, 0, 1, 0, 0, thing format. But then we have it in a format like this. So let's think about what will happen if it's in one hot encoding format. So imagine we have an image which is of class 2, and so and corresponding to this image, you pass the image through your model, and your model gives you a tensor of size 10, output of size 10, which is say a tensor, and it has probability, it has some values, and you apply softmax to it. So now it is probabilities 0 0.01, 0 0.03, and so for 2, let's say it's 0 0.5, 0 0.07, and so on, 10 values. And so your ground truth will, if it's in a one hot encoding format, it will be 0 0 1 0 0 and so on, because it's of class 2 corresponding to 0 1 to second position, it will be 1, everywhere else it will be 0. So this will be your ground truth and this is your output. Now how do you apply? So first and then you take this output and then you apply a log to it according to the formula. That's what you have to do. You apply a log to it, and then and again you'll have a tensor of size 10. After you apply log to it, say you have some output which is of size 10. Okay, let's just put some value here so that we're not confused. Let's just say, okay, so after applying log, we have some output is of size 10. Now what do you have to do? We have to element wise multiply this. You have to element wise multiply these, and then we have to add them. Right, that is what we have to do. But then if you think about it, in the ground truth, except for the position where it's a 1, everywhere it's a 0. So you're multiplying 0 with all these other values. It does not make sense anyway. After multiplying 0, it will be 0, and then adding it, it'll all be 0. So the only position that matters is which position is this probability, because you'll multiply 0 with 0.1, you'll multiply 0 with 0.3, you'll multiply 1 with 0.5, 0 with 0.7, and so on, and you'll add all of them. So none of the other values matter except for which one? Except for this position, except for 0.03. Right? Everything else is unnecessary. And so we can just make use of this, right? We can just directly make use of this instead of converting into a one hot encoding format. We can just say, okay, this image is of class 2, and therefore only the output at position 2 matters. Everything else is not required. And so we'll just get rid of everything else, we'll just use this single value. And if an image has image has a class image has a object of class 7, and then we'll only look at the output at position 7. All the other positions are unnecessary for us. So what I'll do is I'll just say outputs is equal to outputs. Turn the negative. So what I've done here, what have I done here? So I have taken the outputs that correspond to only the targets. So I was telling you earlier, only the outputs that correspond to only the values of the output that correspond to the target matters. So for the first image, the ground truth is 0. So I'll only take this value for the first image. For the second image, it's of the ground truth is 1. So I'll only take this number. Similarly, for this image, the ground truth is 7. So I'll only take the output at position 7. And I'll take all of these outputs and then I'll sum it up, because that's what you want to do. You want to sum it up, and then you apply a minus sign. I mean, it's not necessary to divide by number of examples, but then if you want to keep your loss small, then you can divide it by number of examples. It's a constant, right? It's number of examples is a constant, so you can scale down your loss by number of examples. It's not done here, but you can do it. Okay, so this is your loss, and then you can instantiate your loss. So losses cross entropy cross loss. Let's see what's wrong. Okay. Cool. So now you have an optimizer. Now you have a loss. So you have implemented a custom loss function. I mean, the actual mathematics is not important here. The thing that is important is that you can implement a loss function as a class, and you can have a function called call. And whenever you're passing some input to your some outputs and some input to your loss function, then this call function will be called in here implicitly. And so if you do loss of a comma b, and then this call function will be called on a comma b with outputs as a and targets as b, and it will do all of this mathematics. The actual mathematics is important. Like, what you're trying to learn here is not how to do cross entropy loss. You do some kind of mathematics, you return the loss function, you return the corresponding loss, and then like with the earlier cross entropy loss that is already implemented in PyTorch, you can just do loss dot backward. The exact same thing happens here. You can just do loss dot backward, and it should work. Okay, let's try running this. I mean, I think we should reinitialize the data set, because we iterated through the data loader a couple of times. So, and we have our data set, have your model, have your entropy loss, you have your optimizer, and then you also have your so let's throw this away. Have your everything is done, I think. So let's try running it. Hopefully the loss is not nan. I mean, it's taking more time than before, because now we're dealing with 50,000 images, right? So each epoch is 50,000 32 by 32 images, and also color images. So there's 3 times the data. Earlier it was black and white images, so it is 1 by 28 by 28. Now it's 3 by 32 by 32. So it's like more than thrice the information per image, and you also have 50,000 images. So you can tell how it'll take more time per epoch. Okay, great. So it is calculating training loss, and it's printing it out, and hopefully this training loss will decrease with time. Okay, so far we have done we have learned how to make a custom data set, we've learned how to make a custom data loader, we've learned how to load data and all this stuff we've done, and then we have learned how to make a custom data loss function. And again, I have to iterate that the actual math inside the loss function is not what's important here. It's just the idea that you can make a loss function, we can make a class for a loss function anytime, and you can have a call function inside it that takes in your outputs and your targets and will calculate the loss function for you. So I mean, it could have, so instead of all this mathematics, it could have just returned one here, and it would still be some kind of loss function. It wouldn't be a useful one, but it's still a loss function, and you can instantiate your loss function, and then you can use it as with any inbuilt loss function that exists in PyTorch. And here I'm using a pre-made optimizer. Again, optimizer is also something that you can customly design. If you like come up with a new optimizer tomorrow, you can implement that as well. And yeah, your loss is decreasing, so that means your training is working. So I won't be running this more. I mean, you understand, right? So like, you have seen a model train before, so it's not, I don't have to train it. Okay, so yes.
We're learning how to make like optimizer and this data loader and the loss function, but in the for the sake of this course, for any of the practical models that we'll be making, will we be expected to make these ourselves or use whatever
You can use a
certificate we
predefined, I mean, like, so it depends. So what kind of, if you're doing a new task that nobody has done before, then you will be designing the loss function yourselves. So in case of classification, it's cross entropy is a normal loss function. If you're doing some kind of regression, then maybe L2 loss. All these kind of losses are like very common, right? It's commonly used, and that is why it's pre-built into PyTorch. But in case you're doing a new task, or you want to add some new kind of loss function that you have designed after doing research, in case you design a new kind of loss function, you want to implement it, then you have to, I mean, you can't expect it to be already present in PyTorch, right? So I just wanted to show that you can implement it yourself and use it without any issues. And similarly for optimizer as well, you can do it, but then optimizer, I don't think, I mean, like, actually, so actually designing a new optimizer is actually much more challenging task than designing a new loss function. But then just know that there is the option of doing that if you have to.
Okay.
Right. So did Sir cover any optimization algorithms like gradient descent or something like that? I'm not sure. Can somebody tell me, please? Aditya, has he covered any kind of optimization algorithms in class?
We were doing the back propagation
All right.
last I remembered.
And did
And
he?
I think before that there was some description about gradient descent.
All right. So he basically mentioned gradient descent, right? So I think I can do that
Yes.
then. Okay. So in gradient descent, did you talk about learning rate?
Yes.
Great. Okay. So in our optimizer, you can see here that we've mentioned a learning rate. We've mentioned a learning rate of 0.01. But this is a constant learning rate. So throughout your training, the learning rate will remain same. But what if you want to change this learning rate during training? Then what you can do is you can use something called a scheduler. Either you can use an inbuilt scheduler, or you can make your own scheduler. But let's use an inbuilt scheduler for now. So if you look at the documentation, let's look at right, torch.optim. It's there in torch.optim scheduler, right? Torch.optim.learning rate scheduler provides several methods to adjust the learning rate based on the number of epochs. So during training, if you want to change your learning rate, then you can use something called a learning rate scheduler, which basically schedules the learning rate depending upon what phase of training you're at right now. And there are lots different kinds of schedulers. Learning rate scheduler. Yeah, so there are different kinds of schedulers. There's like, you can have, I don't know if this is visible. Okay, that does not help. So there's something called, constant learning rate is what we've been using so far. It's constant learning rate scheduler. I mean, that's just basic constant learning rate. And you can have a scheduler which like linearly decreases or increases your learning rate. And there's something called step-based decay learning rate. So that does this. And then there's like also exponential decay that exponentially decays the value of your learning rate as with number of epochs or number of iterations. So let's just look at a very basic learning rate scheduler. Let's look at the linear learning rate scheduler. What is a linear learning rate scheduler? It changes your learning rate linearly with a small multiplicative factor until the number of epoch reaches a predefined milestone, which is the total number of iterations. So you can specify. Let's make a learning rate scheduler. So after this, because you need optim for it, so let's call it scheduler is optim dot learning rate scheduler dot linear lr, and you have to pass in the optimizer. And okay, what else do you need? You need a start factor. So start factor is a number we multiply the learning rate in the first epoch. Yes, is somebody asking? Okay. So let's say start factor is 1, is 0.1. Say we just want to change it over 5 iterations, so that for visualization. So what happens is start factor is start. Okay, factor. What am I doing wrong? Total iters, I think. Right. So start factor is 0.1, which means that it will take the learning rate, which is 0.01, it will multiply it by 0.1. So what is that? 0.001. And it will start at that. And over 5 iterations, it will linearly increase the learning rate from 0.001 to 0.1. That's pretty easy, right? It's a very easy scheduler, which it starts at 0.001, and which is a start factor, and then it linearly ramps it up or ramps it down. You can, I mean, based on how you factor your, I mean, how you define your start factor, it will ramp your learning rate up linearly over 5 iterations, so that after 5 iterations, your learning rate is 0.01. And how do you use the scheduler? How do you use the scheduler? I mean, after you declare your scheduler, after one iteration is over, you can just do scheduler.step. After your optimizer.step, you do scheduler.step. It will change your learning rate after how many ever iterations. So that's, yeah. Yes, Aditya.
So in the graph you showed, there was one where the learning rate went down like in a stepwise fashion.
This one, yeah. So that's step-based decay.
This is the one we're implementing.
No, the one we are implementing is this. I mean, not this, but then like this. It's a linear one. So based on number of iterations, it will slowly. I mean, it's not this, right? Like this is like it's constant for some time, it drops. It's constant for some time, and then it like they linearly ramp it down, drop. It's constant for some time, and so on. Here we are like linearly decreasing it. We start at say we start at 0.01, and then we linearly increase it over the number of iterations to 0.01. But then over 5 iterations, it's like a straight line. You can think of it as a straight line.
But it's linear with respect to the epochs, right?
It's so in this case, no, it's linear with respect to number of iterations. If you want to have it with respect to number of epochs, then what you have to wait. Where is it? Yeah, here. What you have to do is you just have to multiply this by number of batches. I think number of iterations. So if so in here you're saying 5 iterations. Over 5 iterations, ramp it up. But then in case you want to ramp it over an epoch, then specify how many iterations are there in one epoch. So in case that we have 50,000 samples and our batch size is 100, then we have 500 epochs, right? I mean 500 iterations per epoch. So just write 500 here, and after one epoch, it will ramp it up.
So what I was asking was, the learning rate is updated after
every
5 iterations.
learning rate is updated when you call this scheduler.step. So if you call it here inside an iteration, it will update after an iteration. So if you call it outside, if you call it here, it will update after an epoch. I mean, yeah, I mean
it's updating
every time you call scheduler.step, it will update it. And how many times will it update it? It will update it for 5. I mean, it was 5 here earlier, so it will update it for first 5 times till it reaches 0.01. After that, every time you call scheduler.step, it will still remain this.
Okay.
I mean, there are various kinds of learning rate schedulers. It all depends upon how each of them function individually. But this is the basic idea. You can have